Hi, welcome back to McClutchy Maths. My name is Natalie McClutchy and this is our second video in our Surds playlist. Today we're looking at how to add and subtract surds. If you'd like to engage further with us here at McClutchy Maths, here are a few ways I'd like to suggest to you. Firstly, like and subscribe and hit that notification bell so you'll know when the next video is available and ready to watch. You could tell someone about this video. If you're a teacher, why not share it with your class on your OneNote? You can follow us on Facebook and Instagram, and one of the new ways that you can engage with us here at McClutchy Maths is to say thanks by donating $2 with the little love heart button to say thank you to us for the work that we put in, but also to help us with the ongoing costs of running the channel. Okay, let's get straight into some principles about what like surds are. Now, as we were looking in our Introduction to Algebra series, we talked about what like terms were in algebra. In algebra, x's can only be added to x's, y's can only be added to y's, and so on. Now, it's the same principle here with surds. Only like surds can be added and subtraction. And if it's to be a like surd, you have to have the same number under the square root sign. So these are multiples of the same surd. So for example, root 3 and 3 root 3 and 10 root 3 are all considered to be like surds. It's this root 3 part that identifies them as like surds. In fact, we call these numbers in the front coefficients as well, just like we did with 3x and 10x. Okay, so those coefficients get added. So this would be a 1 root 3. We just don't write the 1 because we like to keep it simple in maths. So if we're going to be adding these three numbers together, we're going to add just the coefficients. 1 plus 3 plus 10 makes 14, and then root 3 stays as the common thing across, just like we would use with x's and y's. So if we can remember that principle about like surds, adding and subtracting surds is really easy. So this would be 14 root 3 if we added those coefficients together. Okay, here's our first example. Simplify 4 root 6 plus 3 root 5, take away 2 root 6 plus 7 root 5. So what I can see straight away is that there are two different types of surds that are not like surds. I've got the root 6s and the root 5s. Now, a little strategy I use when I'm working with terms that are not like terms and adding them together, if they were x's and y's, for example, is I always circle this first term and then I look for the matching like term, which is this one over here. And then I would circle that one as well, remembering that this sign in front goes with the term after. This is not take away 2 root 6, it's negative 2 root 6. So if I circle that one, that enables me to keep them together. I could even rewrite this with the like terms put together side by side. So I've got the 4 root 6 take away 2 root 6 plus 3 root 5 plus 7 root 5. So now what I've done is just done a switcheroo and brought the like terms closer to one another. So now my focus is just the coefficients. 4 take away 2 is 2 root 6. 3 plus 7 is 10 root 5. And I cannot simplify that any further. If I could, I should be looking here at these numbers here and seeing if I could simplify that. And for more information on how to do that, watch the previous video. Okay, let's look at our second example. I've got 5 root 2 take away root 8. Now, the issue here is that they are not like terms, or are they? Why I can see that these are not like terms, I can actually simplify root 8 and then I've got something to work with. So let's simplify it first. So 8 is made up of 4 times 2. We know 4 is a perfect square. I could take the square root of 4 and I'm going to get 2. So my second surd here will actually be 2 root 2. Now I've got two like terms that I can deal with. Focusing just on the coefficients, 5 take away 2 is 3 root 2. Okay, here's my third example. Now I've got two surds that can be simplified, so I need to simplify both of those before I can make any further progress. So I'm going to recognize that 3 root 20 is also the same as 3 and square root sign 4 times 5. There's my perfect square there. And 45 is 9 times 5, so there's my perfect square right there. So let's simplify that. Square root of 4 is 2, so this is going to be 3 times 2, which is 6. And over here I've got the square root of 9 is 3, so that'll be 6 times 3, which is 18. And voila, I've now got 3 like terms, all root 5s. So now I've got 2 take away 6, which is negative 4, plus 18 is positive 14, 14 root 5. Okay, let's step up some complexity by looking at some fractions now. I know this freaks a lot of people out. Our fraction rules are the same as they always were. We need to have a common denominator to add and subtract any sort of fraction at all. So I need to change these into a common denominator of 15. What that means is I'm going to multiply this fraction here by 5 over 5, which is the number 1, and I'm going to multiply this fraction by 1 as well in the form of 3 over 3. And the reason I'm telling you it's 1 in that form is we're not actually changing the fraction to a different value. We're actually just making an equivalent fraction. Okay, so let's do that. Let's multiply this one by 5 over 5 and this one by 3 over 3. So now what I've got is 5 over 15 is my equivalent fraction here, and 3 over 15 is my equivalent fraction there. So now I've got two fractions with a common denominator of 15. Now I can do the subtraction. Firstly, I can't actually do anything with this 8 because we've got two different surds. They're not like surds. So what I want to do is I want to change this one here. Remember, it's 4 times 2, and 4 times 2 is 2 root 2. So now I've got 5 times 2 makes 10. We don't need to change this one here. So now I've got like surds, common denominators. Now I can do the addition and the subtraction. 10 take away 3 is 7. So I'm going to have 7 root 2 over 15. Okay, we're stepping up our complexity now with a worked example of a worded problem using some of our knowledge about measurement from years gone by. So firstly, it says to find the perimeter of the triangle in simplest exact form. Now we know perimeter means the sum of all sides, and so that's some of our prior knowledge going back to primary school. Simplest exact form may not be something we're familiar with, but exact form means just make sure your answer is in surd form. Otherwise, if the question wanted this rounded, because remember, surds are irrational numbers with an infinite number of decimal places. So if it asked us to round those to a certain number of decimal places, it would state that instead. So that means we're not just putting this in the calculator and coming up with a number that's rounded. We're going to give it an exact form, which is the surd. Okay, firstly, I've got this missing side here. How can I work out the perimeter of this triangle if I don't know the length of this missing side? Well, it's a right angled triangle. So I'm also activating some of that prior knowledge going back to about grade 8, where I'm going to use Pythagoras' theorem. Now you'll recall from Pythagoras' theorem, it's equal to c squared equals a squared plus b squared. So what I'm trying to find here is this hypotenuse, which is the value c. So what I'm going to do is substitute in the information I've got, which is the square root of 3 squared plus the square root of 27 squared. Now you'll remember from our previous video that squared cancels out the square root signs. So that means I can cancel here, cancel here. I'm simply going to be c squared equals 3 plus 27. And 3 plus 27 is 30. So now that's my surd form for this side of the triangle, root 30. So now what I need to do is find the perimeter, and which means I'm going to add all three sides. Before I do that, I want to have a think about, are there any of these surds that I can actually simplify to enable me to add like terms together? Now, if we look here at root 30, for example, well, it's got a factor pair of 3 times 10. Neither of those are perfect squares. It's got a factor pair of 5 times 6. Neither of those are good ones to be working with either. So root 30 can't really simplify it. Root 27, on the other hand, we can. It's made up of 9 times 3. We know 9 is a perfect square. So what we're going to do now is we're going to simplify these numbers. So I'm going to make this one here into 3 times 9 under the square root sign. And then if I take the square root of that, that will become 3 root 3. So now I've got two like terms that I can add together. 1 root 3, or just root 3, plus 3 root 3 makes 4 root 3, and plus 30 meters. And I can't simplify that any further. Okay, this one's a bit of a doozy. I got this out of a very advanced textbook for senior mathematics. So if you're not at that stage yet and you feel like you can deal with it, then let's deal with it together. Okay, so let's have a look at this yellow line here first. I've got half of the square root of 100 a cubed b squared plus ab root 36a minus 5 root 4a squared b. So I've got algebra going on, I've got fractions going on, I've got square roots, and I've got my index laws going on as well. So I want to have a look at all of these things. So let's just try and break up what's going on under our square root signs. So we know 100 is made up of 10 times 10. It's a perfect square. A cubed is made up of a squared times a. You'll notice with any of these ones that have got odd numbers, break one out and drop that power down one and you've got a perfect square. And then I've got simply b squared. I've got over here 36 is a perfect square, 6 times 6. 4 is a perfect square, 2 times 2 times a squared b. So we can simplify this a little bit further now. Let's take these numbers out the front. So I've got the square root of 10 times 10 is simply just 10. So half times 10. This a squared, if I take the square root of that, I'm simply going to have a. B squared, the square root of that is simply b. And the only thing I can't take away from the surd is this root of a. Let's have a look at this next one over here now. The square root of 36 is simply 6, so it will go out the front. And the b, AB here, stays out the front. This a on its own will stay under the square root sign. Over here, the square root of 4 is 2, so it will come out the front. The square root of a squared is simply a. It will come out the front of the surd. And the b stays under the square root sign. So I've simplified this a little bit further. Now what I'm going to do is a few things here, like half of 10 is 5. I can work that through that. And I'm going to get rid of all these multiplication signs, basically. So I've now got 5ab, root a. And then out the front here, I'm going to have 6ab, root a. And then negative 5 times 2 is negative 10a, root b. So now I can add and subtract some like terms. Square root of a, square root of a, they are like terms. Square root of b, not a like term, so it will be a standalone. So 5ab plus 6ab makes 11ab. Root a, take away 10a, root b. That was a tricky one. You might want to pause through that and just think through those steps of working, or even rewind the video and watch that little bit again. This would be about as hard as it gets in a year 11 or 12 exam. So if you could do any variations of these using algebras and combinations of simplifying surds, you are almost all the way there. Well, if you've got any questions about anything you saw today, mcclutchymass@yahoo.com is the best place to reach me. If you'd like some more complex examples like that to be sent to you, you could ask me via email and I will happily send you some extra questions to practice with. Although I'm sure your teacher has access to the same resources, but I'm also helpful with that way as well. Well, you've been watching McClutchy Maths. I'm Natalie McClutchy. Have an amazing day.